This lesson is going to look at how we extract metals that we would consider very reactive using a technique called electrolysis. The SQA learning outcomes we're going to concentrate today are going to be these ones at the bottom, involving electrolysis and the details about this method of extraction. So as we saw in the previous video, for extraction of copper, lead, tin, iron and zinc, you can extract them by heating with carbon or carbon monoxide. However, this method will not work for more reactive metals. For more reactive metals, such as potassium, sodium, lithium, calcium, magnesium and aluminium, more energy is required to extract the metal and break those ionic bonds between the ions. The technique we use for this is called electrolysis. The definition of an electrolysis is the decomposition, i.e. breakup, of an ionic compound into its elements using electricity. The word electro obviously means electricity, the word lysis means to break up. We're going to use copper chloride and tin chloride as examples. These aren't the most reactive metals, but these are simple to do for the examples we're going to look at. You saw in the last video how we could extract copper from a drop of copper chloride solution. So this is looking in a bit more detail what's happening. At the positive electrode, it will attract negatively charged particles such as these chloride ions. So the chloride ions will move towards the positive electrode, and the positive electrode will remove an electron from that chloride ion in an oxidation reaction. Because chlorine doesn't exist as individual atoms, it will come together as a chlorine molecule being diatomic. So we need to double everything. So you can see this is the overall equation that we got. So we see bubbles of chlorine gas, as in the video here, being produced at the positive electrode. At the negative electrode, that will attract positively charged copper ions. The copper ions will gain electrons from the negative electrode. You can think of a negative electrode as a source of electrons. So this positive copper ions will gain negatively charged electrons to form neutral copper atoms. So if I click on this little animation, you can see these are the bubbles of chloride gas formed at the positive electrode in an oxidation reaction. And this reduction reaction that we can see here is causing copper atoms to form at the negative electrode. Here is an example using tin chloride this time. So as before, the chloride ions move towards the positive electrode, and the positive electrode removes an electron from the chloride ion to form chlorine atoms. Chlorine atoms pair together to form diatomic molecules, so we see chlorine gas being formed as part of an oxidation reaction. So we see bubbles of chlorine appearing around the positive electrode. The positively charged tin 2 positive ions will move towards the negative electrode. The negative electrode will give those tin 2 positive ions 2 electrons, so the tin ions become tin atoms, and we see tin formed at the electrode. Here's the video showing what it would look like if you did it in a drop of tin chloride. So here's our 2 electrodes. This is our negative electrode, so the tin ions are moving towards this negative electrode and are gaining electrons, and you can see that the tin atoms are starting to form around it. You can even see crystals starting to form around here. This video should zoom in and show you what it looks like. So they're quite picturesque looking. These shiny tin crystals of tin metal are appearing as part of this reduction reaction occurring at the negative electrode. So here's a summary of how electrolysis works. I'm going to use sodium chloride as an example. The thing to note is the negative electrode is negative because it's a source of electrons, and it will give electrons to positive ions such as, say, sodium ions, which we have here. So say we have sodium ions in the solution. The negative electrode will give an electron to the sodium ion, changing the sodium ion to a sodium atom with an electron arrangement of 281. In terms of the chlorine, it will have already gained an electron to form a negative charge. It will lose an electron as the negative electron is attracted to the positive electrode to form chlorine atoms. So to summarize, positive ions gain electrons at the negative electrode, and negative ions lose electrons at the positive electrode. These are from the SQL learning outcomes for electrolysis, so you need to know the definition of electrolysis, i.e. it's the decomposition of an ionic compound into its elements using electricity. One thing I didn't mention is that a DC supply, a direct current supply, must be used if the products of electrolysis are to be identified. So you only get one metal formed at one electrode and one non-metal formed at the other electrode, for instance. The positive ions, remember, gain electrons at the negative electrode, and negative ions lose electrons at the positive electrode. So here's an example of how we get aluminium from its molten ore bauxite. We have, because ionic compounds don't conduct electricity, the ore has to be made into a melt. Because if you remember from the section on conductivity of ionic compounds, they do not conduct when solid because the ions can't move. The rocks need to be melted to make a molten solution to allow the ions to move and conduct electricity. Once the solution is molten, this reaction occurs at the negative electrode. In aluminium oxide, the aluminium 3 positive ions will gain 3 electrons to form aluminium metal. And at the positive electrode, while oxygen ions will have a 2 negative charge, they will move towards the positive electrode and lose 2 electrons in order to form molecules of oxygen gas. Here are some exam past paper questions for you to try. So pause the video and see if you can get the correct answers. The term used to describe the structure of a solid strontium chloride is an ionic lattice. It's a metal joined to a non-metal. You would not get the mark if you mentioned covalent network or metallic bonding. Why do ionic compounds like strontium chloride conduct electricity when molten? It's because the ions are free to move. Do not say the electrons are free to move. The localized electrons would be free to move if it was metallic bonding. Pause the video and have a go at these questions. Okay, the clue to the answer in this is the words lose electrons. Whenever I see the words lose electrons, the first word that should come to mind is oxidation. Explain why a DC supply must be used. The acceptable answers for this would be to allow the products to be identified. So you can see, for instance, say copper at the negative electrode and chlorine at the positive electrode, to make sure there's only one product produced at each electrode, or to separate the strontium from the chlorine. Those are the acceptable answers. You would get 0 marks for any of these ones that you can see at the right hand side. So to summarize the extraction of metals, for mercury, silver and gold, heating alone will allow you to extract the metal. It will not work for more reactive metals going from potassium to copper. From anything going from gold to zinc, heating with carbon or carbon monoxide will allow the extraction of the metal from its ore. However, for the most reactive metals such as potassium, sodium, lithium, and alkali metals, and calcium, magnesium and aluminium, electrolysis is required. Lots more energy is required to extract those metals from their ores. So that's a summary from the SQA of all the things you need to know about extraction of metals.